Welcome to the mini lecture on the first law of thermodynamics. So many of you guys might have heard this before. First law of thermodynamics simply states that the total energy of the entire universe is constant. So what we're going to do in this section is explore this concept, what it means, some of the implications, and ultimately see how we can apply this concept to the field of chemistry. So let's start off with a quick recap of what we just talked about. Essentially, in our introductory video, we defined a number of key terms. Okay, we talked about the concept of energy and how energy is this capacity to do work, and how energy comes in two flavors, kinetic and potential. We defined a term internal energy. We used E to denote the internal energy of a system, and we defined it to be the sum total of all of the kinetic and potential energy contained within that system. And we saw that this delta E, the change in internal energy, is path independent because the internal energy is a state function. We used the example of altitude to explore that. And we introduced work and heat as forms of energy transfer. Work involving energy transfer using macroscopic modes of motion. You can see it happening. And heat involving microscopic modes of motion. You can't see, water being heated up, or faster moving gas molecules as you heat them up, because we can't see that molecular level motion. We're talking about microscopic modes. Okay, and then finally we define this concept of a system, whatever part of the universe we care about, and the surroundings as everything else. Okay, so with that, we're in a position to start building up this first law of thermodynamics. So the first thing I want to put out there is this concept of a change in internal energy. So we said that internal energy is a state function, okay, which means that we can define any change for any physical, chemical process, whatever, as delta E, right, by just looking at the final and initial states. We don't care how the system got from one state to the other. Okay, so here is the first law of thermodynamics stated mathematically. So what the first law says is that the total energy of the universe is constant. In other words, if we look at the delta E of the universe, it must always be equal to 0. Now remember, the energy of the universe is equal to the energy of the system plus surroundings. Okay? So if we take the delta E universe, then we can form delta E system and delta E of the surroundings. And we know delta E of the system plus delta E of the surroundings is going to be equal to 0 by the first law. Then there's an alternate definition of that first law of thermodynamics. Namely, that the energy of the system is always going to have the same magnitude but opposite sign as the change in energy of the surroundings. So both of these definitions are in fact equivalent. So take a minute here and go back through that, maybe listen to the video again and make sure that you understand why both of these definitions are equivalent forms of the first law of thermodynamics. So to look at some examples involving this first law of thermodynamics, and okay, so we have this concept that energy of the system, right, the change in energy of the system is equal to the negative of the change in energy of the surroundings. So let's suppose we have some system, I don't care what it is, some general system in an initial state with an energy right here. Okay, if the final state has a lower energy, then that means that the system is losing energy. So delta E of the system is going to be negative. Okay, so final minus initial, final is less than initial, we get our negative delta E of the system. Well, that energy must have gone somewhere, and the first law of thermodynamics basically tells us that the change in internal energy of the universe is constant, which means that energy can't have just been, we can't create energy and we can't destroy energy. Okay, so if that energy can't be created or destroyed, it has to go somewhere. Well, it's going to end up being released to the surroundings. Similarly, if we start off with a system in some initial state, we go to a higher energy state. Well, that energy must have come from somewhere. And in this case, that somewhere must be something in the surroundings. So the energy must be absorbed from the surroundings if we have a positive delta E associated with that system. And so when we are talking about energy transfer processes, well, in the previous lecture, we laid out some definitions, a couple terms, Q and W, heat and work, that are our methods of energy transfer. So if there's any sort of energy change occurring in the system, then that total energy change is going to be the sum total of all of the energy transferred using microscopic modes, heat, and all of the energy transferred using macroscopic modes, work. All right. So an example here, we can go back to burning octane. If we start off with intact octane molecules and some oxygen up here, they're going to have some energy that is right up here. Okay. And of course, if we burn that octane, we're going to end up with CO2 and water, and we're going to release energy, which means the energy of the molecules, the product molecules, must be lower down here at the bottom. Okay. And of course, the energy difference between these reactants and products will tell us how much energy is being released. But this energy could be released in many different ways. If we just put a bunch of gasoline in a trash can and light it on fire, then the vast majority of that energy is coming out as heat. Okay? So we have basically heat being released. So everything's shown up as Q. If we burn it in a more controlled fashion in the context of a combustion engine, then certainly heat will still be released, but you're also going to have energy being released as work. So you're going to get Q and W at the end of the day. But in both cases, the delta E of the system is fixed. So Q and W are not state functions, right? They very much depend on the path that you follow, namely burning stuff in a trash can or in a combustion engine, right? But when you add the heat and work together, you get the total change in energy of the system, and you get a state function. So honestly, one of the parts of this lecture that folks will struggle with is simply keeping track of signs. The equations and the concepts are relatively straightforward, but keeping track of the signs can be a little bit confusing. So we saw in the previous example that when we're releasing energy from the combustion of octane, then there was a negative delta E for that system. Okay, so that goes right along lines of the sign conventions that we are going to adopt. So the convention is to assume the sign of the energy from the perspective of the system under investigation. So if energy is being transferred into the system, then the delta E is going to be positive because the system is going to end up with more energy at the end of the day. If energy is being transferred out of the system, then we're going to have a negative delta E because at the end of the day, this system's ending up with less energy. And we're going to map the same convention on to both Q and W. Okay, so if heat is being absorbed by the system, then we're going to have a positive Q. Okay, so the first two options here, heat is being absorbed in both of these cases. And if heat is being released by the system, then we're going to have a negative Q. Okay. Similarly with work, if work is being done on the system, then we're going to have a positive W. Because if work's being done on the system, then the system is gaining energy. If the system is doing work, giving energy to something else, then the sign is going to be negative. So this little table here essentially breaks down all the different possible, four different possible options you could have. You can have heat being absorbed and work being done on the system. In this case, you're guaranteed to have a positive delta E. Okay? You could have a situation, however, where heat is being absorbed by the system, but the system is actually doing work on the surroundings. In this case, the relative magnitude of Q and W are going to basically dictate the sign of delta E, because remember, delta E is Q plus W. So whichever one's bigger is going to determine the sign. Similarly, if you're releasing heat, but work is being done on the system, right, the relative magnitude of Q and W is going to determine the sign of delta E. However, if the system's releasing heat and doing work, then you will be guaranteed to have a negative delta E. So let's just look at a couple quick examples here. Let's suppose we start off with some hot water, okay, and we set that hot water out on the counter, okay. Then that means that the surroundings, room temperature, right, the temperature of those surroundings is going to be less than that of the system. So we know that the energy is going to be transferred then from that system to the surroundings. And so the system itself is going to be losing energy as that water comes down to room temperature. So it's going to have a negative delta E. And there's no work being done in this example. So Q is going to be energy released to the surroundings. So Q is also going to be less than 0. Okay? Conversely, if we start off with, say, cold water, so ice water in this case, down here at some low initial temperature, and do the same thing, set it out at room temperatures, and then over time, the temperature of that ice water, as all the ice melts and then the cold water warms up, that water sample will eventually hit room temperature. So in this case, the system, being this initial ice water cup, is going to be gaining energy. Okay, so delta E is going to be greater than 0, and that energy is coming from the surroundings. So the energy transfer in the form of heat, and using these microscopic modes, is going to be greater than 0 because the system itself is ending up with a greater degree of thermal energy at the end of the day. Okay, so now let's look at an example involving work. So let's say we have some initial sample where you have a bunch of solid that is releasing gas. It's being converted from a solid to a gas phase. And so you can see the little gas bubbles, purple, building up in here. And as these gas bubbles build up, this system is hooked up to a contraption here that allows this piston, right, to be the same closed system. So as the gas builds up in this chamber, then that piston is going to be pushed back. So this system is now pushing against some outside pressure, P surroundings. Okay, so in this case, the system here is doing work on the surroundings by moving this piston out. Okay, and as a result, this system is losing energy. So delta E is negative because in the final state, the system has lost energy and it's put that into the surroundings. So you're going to be getting a W that is less than 0. Now let's say we take the system that we just formed here and we then apply an external pressure that is sufficient to compress that gas back down. Well, in this case, you're going to have to do work on the system. So doing work on the system is going to be adding potential energy, right? And so you're adding energy to that system, so the work is going to be 0 or greater than 0. And of course, the net energy, delta E, the net internal energy of that system will be increasing. So let's round out this discussion of the first law of thermodynamics with a fun practical example. And we're going to use the example of a potato cannon or a potato gun. So some of you guys might have some experience with this. Hopefully it was a safe experience. Basically, a potato cannon is a device where a potato is stuffed into a long cylinder and it's capped at one end. So basically a long cylinder capped at one end. So we're going to cover this thing off. And we're going to put a potato in here. So that's my potato. Okay. And at the other end, we're going to put some sort of fuel. So we're going to put some combustive compound in here. Okay. And what ends up happening then is you somehow ignite this material, this combustive material, and it's being ignited because remember this is capped off. We got a potato jammed in there, so we've got a sealed little chamber in here. So the result of this combustion is that this potato shoots out of that long cylindrical tube, and it can literally fly hundreds of feet. So as this process occurs, the cannon is of course emitting a lot of heat to the surroundings, so the thing gets really hot on the outside, and energy is being transferred into this flying potato. Okay, so with this little picture in mind, let's consider the following example. Let's say that the burning of that fuel, whatever fuel we decide to put inside that potato cannon, let's say it performs 855 joules of work on the potato, okay, and produces 1,422 joules of heat. I want to figure out, we need to figure out what delta E is for the burning of the fuel. So go ahead and take a second and try and answer that. Okay, so hopefully right off the bat you guys recognize that we're going to be using our delta E equals Q plus W equation in order to solve this. Okay, now the tricky part here is the sign convention. Okay, so we need to be very careful that we identify what the system is. Okay, so in this case the system is the fuel. Okay, so we're looking at delta E for this fuel. And we now need to look at this problem from the standpoint, from the vantage point of the fuel being the system, and assign the signs of each one of these Q and W terms appropriately. So we know that Q in this case is going to be 1,422 joules. Okay, so we can write 1,422 joules. Okay, and now this is 1,422 joules of heat that this fuel is producing. So that means the fuel is giving off that amount of energy, right? Which means the net energy of the fuel is going to be less, so this is a negative sign. Okay. Now similarly, if we look at the work term here, okay, so Q plus W, work, we're told that the fuel is performing 855 joules of work on the potato. So the system here, the fuel, is performing work on something else, on the surroundings. In this case, a lot of it ended up in that potato. And so this is going to be another negative term. So at the end of the day, we're going to end up with a delta E of negative 2,277 joules. So that represents the sum total of all the energy that was given off by this fuel. Some of it went to heat, some of it went into that flying potato. Okay, so now that we have an appreciation for these energy transfer processes, in the next video we are going to look at another example that's of even more direct practical importance, which is how do we measure energy? How do we measure energy transfer processes? So that's going to bring us to a discussion of the so-called technique called calorimetry.